Thank you for coming again to my talk from yesterday. I'll do another one about Linux. Today we're going to talk about Linux kernel keystore. Who here actually knew that Linux has a keystore? Oh, some people, nice. So maybe I'll try to make it more interesting. So a little bit about myself first. My name is Ignat. I work at Cloudflare. I do Linux at Cloudflare. I'm a die-hard Linux fan, actually. That's why I'm presenting from a Mac. On Linux, like, it wouldn't be that easy to connect and the screen is there. No. I know, too much. And yeah, enjoy system security and performance, doing low-level programming, Linux kernel drivers, bootloaders, and other stuff written in safe programming languages. For the purposes of this talk, I'm also a fugitive programmer. Probably some of you as well, because, well, not so recently already, like US, NSA, then C and C++, a couple of years ago, I think, right? So it's basically, they had a publication that say NSA recommends that organization use memory-safe languages when possible and bolster protection through code hardening, blah, 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 based on some research that most bugs were memory bugs. And it's a little bit applicable to our talk and where a keystore can help as well, right? So let's talk about application keys in memory first. And to talk about the keys, let's rewind a little bit and go through the operating system concept called memory address isolation. Who here was at the last talk yesterday here about Zephyr versus Linux OS? And it was briefly mentioned there, the advantage of Linux is it's a real operating system, unlike the others, right? So it provides a nice feature called address space isolation. You don't get it. And what does it mean, right? So obviously you have a multitasking operating system, so you have several processes, right? And each process has their own memory region where it operates. So, and once it's located there, so you usually have your main logic, right, your business logic of your application. You have if you use some kind of libraries, it's also there, mapped. Your program or application has a data section where you store global variables and state. And obviously, because you have function, you have stack or multiple stacks if it's a multi-threading application. And it all runs obviously on some kind of kernel, like Linux kernel. You have the kernel specs here. And in kernel you also have the code of the kernel itself. You have static and dynamic data, right? So like constant data and state. You have the driver's code in the kernel space. And you also have kernel stacks. And the core idea of memory address isolation in the operating system that within these memory regions, within the process, like everything can access everything, right? So like my code can access anything from that thing, and same actually within the kernel itself. So everything has access to everything. Kernel address space is flat, and this is why it's kind of very dangerous to load third-party drivers because they will have access to all your system. Anyway, but you cannot access from one address space to another, so you cannot easily go and poke the memory of another process, right? And similarly, you cannot easily go and poke the memory of the kernel from user space. So you have, if you just reference that memory, you'll get an exception, and the operating system and the CPU will not allow you to do it. Okay, so far. So now let's actually zoom into a process address space and let's expand what's in the data section, typically, right? So like, what can you have here is like you have internal state, right? So you have your variables, global variables. You may have a user or customer data if your application processes it, like you download it from somewhere, do some processing, it stays in that memory, right? And the most importantly, if your application does some sort of encryption, like a TLS web server, SSL web server, and cryptographic keys, right? And this is where not all data is created equal, right? But the problem is if your code is compromised one way or another, like your main logic or the libraries you use, basically this whole data section is compromised, right? So like if somebody controls that code, they can, they can access anything within your process address space, they can go and poke and steal that data. But again, not all processes are created equal, so what if application state is compromised, right? Well, it depends. Like, it can be good or bad. For example, if the application state can control the program execution somehow based on your logic, well, it can lead for code compromise, but maybe it's not that bad. Somebody can read your internal variable or counter. I mentioned this yesterday as well, like what if user or customer data, it's much worse, right? Everything is on fire and you get a lot of lawsuits. Well, yeah, it's a big mess, but still it's not fully end of the world. That company still exists and it's very successful. Cryptographic key compromise is total game over. Like, imagine you get a private key for google.com and you can now pretend to be google.com everywhere on the internet, right? How fun is that? So it's a full data integrity compromise, full security compromise, total identity takeover. So it's really big. So from this we can make a conclusion that, like, you know, like of all the data that is processed in your application, you should like try to protect keys the most, right? And how can you do, like, how can your code in a high-level view steal keys? So, like, usually it's some kind of untrusted processing, untrusted inputs, or out-of-bound memory access. So imagine you have like stuff in your memory, and next to that memory you can have your cryptographic key, right? So, and your code may be programmed in a way that it should access stuff, but because it's one same memory address space, if your code is buggy and susceptible to takeover, somebody may direct your code to actually move past that boundary and read the cryptographic key. Who here remembers Heartbleed? Yeah, everyone. This is basically exactly what happens. So processing a custom input, right, and stealing cryptographic keys. So buggy code is one way to read keys or any data, right? Second one is like arbitrary remote code execution. No example here. There's nothing to talk about. If somebody can control your code, they control your data, right? So they can do whatever they want. Probably an example here is log4shell. Remember log4shell, right? Buffer reuse. So this is like a complete C program. You can copy paste later from the slide and compile. And it's quite simple. So you have your main function there, and it does two stuff, like encrypt and then log completion, right? And these two functions, stub function, I'm implementing here, but there is a bug here, right? So like this one. So I suddenly forgot to initialize my message, right? In the log completion. So technically, if you don't have any compiler protections enabled, and you basically compile this code and execute, you'll just notice you accidentally leak your cryptographic key from the encrypt function. So what happened here is basically you have the process thread stack, you have the main code, then you call your encrypt or decrypt function, and somehow you get your cryptographic key, you put it on the stack, right? And you basically finish decrypting data, the function exits, but the key stays, right? So, and the next time the log function takes over, it has basically access to the same memory and accidentally leaks it, right? So, and that's why if you're like working with compliance and security, you will really always find this requirement that if you use some kind of cryptographic keys, your code should always zero out the memory after it's finished using. And yeah, you can for both stack and heap, but it's actually easier said than done, right? Like, if you do it in C, it's kind of like possible, but go and try to do it in Java or Go, right? Where like stuff in memory is copied all the time by these memory management. So like it's very challenging in garbage collected language. And it's all like, and also your code has to actually execute before it can zero out the memory. What if your application just crashes before it's able to do so? So you have like in excessive logging, core dumps, PDB, ptrace, for bugs. Your application may exit earlier than it is able to zero out the memory, right? Yeah, I mean, just don't write bugs, like good code, right? Okay, so obviously this is not a great solution, right? We cannot not write. We want to write bugs, so to have conferences, to talk about what can we do? Well, so obviously we cannot protect all the data reliably, but what can we do, like for cryptographic keys specifically, right? Because this is the most important piece of application data you want to protect. What if we kind of like piggyback on the concept of address space isolation? What if we just, instead of one process, we create another process, we move our keys here, right? And we will, and we define like very small cryptographic logic, which will enable us to use that key, and we will do like some well-defined, very constrained interface to use that key, right? And I call it like the key agent model. Who here uses SSH agent? Right? So yeah, this is exactly partly why it exists. So you put your keys into another process with a small, well-defined interface. You have like your main process is network-facing, rich code, and probably has more bugs. And your keys are stored in another process, which is like more tightly reviewed with a very tight interface and protected, right? So, and the main process does not have access to the cryptographic material, and it's ensured by the address space isolation. And main communicates with the agents with this well-defined interface. And main process can process these untrusted inputs, and agents does not process untrusted inputs. And it's never network facing, so it's very hard to get. Yeah, and as I said, the example of these are SSH agent, GPG agent, and other stuff. But there is a drawback to that model, right? So like if you're following that model, you actually now need to develop two applications, and you need to actually design this well-defined interface. It's very easy to design a well-defined interface, right? You actually need to think about how these two processes will communicate and cooperate. So is it like a Unix domain socket, a shared memory, whatever. And maybe, which SSH agent actually doesn't do, how to design ACL. So like if my process keeps a key, how do I authenticate the remote connector, right? So like actually, in SSH agent, anything on the system can connect to your agent and ask it to use a key, which is not great. This is where we come to Linux. The official name is Linux Kernel Key Retention Service, or I call it Linux Kernel Keystore. So, and what it takes this idea, right? And what if we replace the process 2 with the kernel? It's a dedicated address space, right? And it always runs. If it doesn't run, your computer doesn't run. And it's the well-defined interface is system calls, right? It's very well hardened and uses the system. So this is like exactly what it is. It's basically a feature in the Linux kernel which allows you to store cryptographic keys as kernel objects. And it was actually initially designed for in-kernel encryption services like disk encryption. So because you encrypt, when you encrypt disks with your Linux kernel, the Linux kernel actually needs a cryptographic key to perform the encryption. So you need to somehow pass it to the kernel. So it was an interface to pass keys to the kernel. But then eventually it got extended to user space, that user space programs also can use it to store their keys and services. And the nice thing is that the keys are stored outside of the main process address space, and you have a well-defined system call interface already. Because the keys are now kernel objects, the kernel can enforce different ACLs, similar to the way how the kernel enforces ACLs on files, or like the keys can have different permissions. And the nice thing about it is that also as kernel objects, they have a key lifecycle. And the key lifecycle is implicitly bound to other kernel objects like the process or something else, so the keys can be actually automatically destroyed by the kernel if the respecting holders are not needing it. Surprisingly, for a kernel feature, it has good documentation as well. Yeah, so, and internally, like the keystore supports keyrings and keys. So keyring is a collection of keys, basically, and it can contain either keyrings, and keyrings can contain keys. Right? It's kind of similar to a file system structure. And the difference is like the keys contain actual cryptographic material or a pointer to it or a handle to a cryptographic device. That's also possible. And they can be, you can read and write keys and use keys to do cryptographic transformations. There are several key types. I will briefly go in the future, usable, one, asymmetric, encrypted, and trusted. And they are kind of similar to a file in the file system with actually the key contents. And keyrings, they basically contain links to keys and other keyrings. So, and they represent a collection of keys. There, you can explicitly create a key ring, or you get some system default key rings, which I go back, which I'll describe a little bit later. The key rings are actually enforce the lifetime of the key. So a key should be linked to at least one key ring. If a key is not linked to any key ring, the key is automatically destroyed by the operating system. And key rings are similar to a directory and file system. So let's see like a very baseball example, like everything else in Linux, like the system call interface has a nice command line wrapper, so we can use it in the shell. So here I use the keyctl utility, creating a new keyring called myuring and linking to my implicit user keyring. And both keys and keyrings in the keystore, they are referenced by this unique serial number. So now I can actually add a secret or a key to my new keyring with the data hunter too, right? And yeah, and here I can show that my key hierarchy. So I have the session keyring, underneath I have my user keyring, my custom keyring called my ring, and my key. And yeah, all the IDs here. And also because I created this key, I have all the rights to that key, right? So I can read it back, so I can actually read the data and see my secret data is hunted too. Like more interesting example is like key sharing or secret sharing between two users on the system. So here is an Alice and Bob, and you can see they basically don't share any credentials. So they're not part of the same group, nothing. They're like two distinct users on the system. So what Alice can do, she can create a new secret, and imagine like Alice wants to share the secret with Bob. So what Bob can do, Bob can create a new keyring, call it from others, and then Bob can basically set permissions on that keyring, allowing everyone on the system to write that. So write means putting keys in that keyring. And Bob can basically communicate the serial number to Alice. What Alice can do, Alice can move her key to the Bob's keyring. So now we see that Alice doesn't possess the key anymore. And actually Bob can now read the key and get the secret. And Bob, because Bob possesses the key in his keyring, so Bob has the permissions to the key. Even though Alice created it, she moved it away and like she doesn't have access to it. Yeah, so, but this is where like keyrings become really powerful with special keyring types. So there are like process-bound keyrings called session keyring. It's a keyring automatically created by the system for the current process and all the child processes. The process keyring, so every process on your system can have its own private keyring, and even a thread keyring, so like a keyring private to a thread. So imagine you have a web server, and you have, let's say, one thread per, and you service multiple domains, and you have one thread per domain. You can even like store keys in the thread private keyring and serve these domains independently without the risk of the key being exposed to the logic of the other domain. There are user keyrings. So user keyring is shared between all the processes with a particular user ID, and there is a user session keyring. There is like some semantic differences, but not important. store. There is also like persistent k-rings, which is one, it's confusing for people starting with this because they thought it's kind of somehow stored on persistent media. No, persistent because the lifetime of that keyring is not bound to a kernel entity, but rather than to a timeout. So it's very useful because other key rings are getting automatically destroyed when like a process dies. These key rings are used for things, let's say like you have a cron job, which like process starts and ends in a time intervals, but it has to have access to some key. So you can actually use a persistent key for that. And if like your cron interval is 5 minutes, but you set a timeout for that key for 10 minutes, as long as your cron job is working, your key will be accessible. But if for some reason your cron job will stop restarting, then your key will be securely destroyed by the operating system. So, and this is where this example, by the way, all this was copy-pasted from a real terminal. So this is a demo, but it never fails. So. But we can literally copy-paste all these commands and try them yourself. So yeah, let's show like how lifetime of the keys is working well. So I will use my session queuing. So I'm adding a secret to my session queuing. So yeah, I have a new secret here with this idea. Yeah, I'm SSH now to this machine, right? So what I'm trying to do in another terminal, I'll put a BPF probe on a kernel internal function which is responsible for destroying the key, right? So I'm just monitoring that function. And now, what I do in the first terminal, I just exit my SSH session. So I logged out of the system. What the system does, it automatically destroys my session keyring because remember the session keyring is bound to the current and all the child processes. So my current process, SSH process was killed. So the kernel automatically destroyed my keyring, and because my secret wasn't that keyring, it also automatically destroyed my secret. So this is very useful, right? So it will always work when the process dies, even if the process is up, the application like abnormally crashes. You will always get your keys destroyed and the memory nullified. So I can reconnect back, and I can see that I don't have the secret anymore because it was destroyed, and I can also see that the session keyring ID is different because the operating system under the hood destroyed and recreated my session keyring when I logged in next. So this is where the power comes from. Like if you select the appropriate keyring type, you can ensure that your keys will be securely destroyed when not needed. And even if your application crashes, and even if you use garbage collected languages. So as long as if your process dies, your keys get destroyed. Like you're compliant and secure. Good. So what about different key types? So far we've been using the simplest key type called user keys. So you have my user key, I have my cryptographic date or my secret. I can put it in the kernel, and either myself or another process, if it has appropriate permissions, they can read the data back. There is a special key called logon key. It's very similar to user key, so you have your cryptographic material, you put it in the kernel, but you can never read it back. And why it's useful, it's actually this original use case for the kernel keyring to pass cryptographic material directly to the kernel, so you can like use disk encryption. If you run a recent Linux distribution and you use disk encryption, you will probably notice that the password you entered is passed to the kernel through as a logon key type disk encryption. There is also asymmetric keys. So imagine you have an RSA key, right? So you can put it into the kernel, and instead of reading back, if you have appropriate permission, what you can do is you can actually decrypt or sign data. So this kind of turns your kernel into like the software HSM or YubiKey thingy, where like you can have one process distributing keys to the kernel and another consuming processes just using the key without needing even to see the cryptographic material underneath. So here is an example. So you can generate a private RSA key. You need to actually converted to BTCS8 format because this is how the kernel understands it. Yeah, and you can push it to the kernel and then basically use it to sign some data. Yeah, I can show here that with OpenSSL I can actually verify the signature. And now, because you can store the RSA key, I will send this link again at the end of the post, but we even made like a prototype patch to OpenSSH. So instead of running an SSH agent, you can literally just insert your SSH key into the kernel, and your main SSH process, we use it to actually authenticate to remote systems. So you literally have the same user experience and security as you run an agent, but you don't need to have an agent. And you can improve it by actually restricting what processes can access this key, so you can have the proper security around. Okay, so with the basic feature, like how can we use a key store as key management building block? So in Cloudflare, we're running a huge infrastructure. There's a lot of keys and secrets flying around, right? So we need to somehow distribute these keys to all applications and services that we support. So the big question now that we care about is how can we actually provision application keys without cryptographic material ever being exposed to user space applications. So because in the previous example we saw, even though I put it in the kernel, the application still has access to cryptographic material, at least initially, it needs to insert it to the kernel. And there are several ways. There is a concept called encrypted keys. So what it means, like imagine you already have some key in the kernel called a wrapping key. What your process can do, it can take like an encrypted key, a wrap key. Wrap key means it's a cryptographic key encrypted with this wrapping key, a wrap block. So the process actually doesn't see the plain text key, it only has the block. And it can insert it into the kernel, and the kernel will automatically use the wrapping key to unwrap that key. So it's kind of plain text in the kernel space, but never in user space. And when you try to read it back, it wraps it again automatically. So you can never extract the plain text here. But you can see the problem here, right? The chicken and egg, how they get the wrapping key inside the kernel, right? So, well, one way you can do it, you can replace the wrapping key with the TPM. And again, you have the wrap key, it's called trusted key, so you have the wrap key, you can insert in the kernel and the TPM, the system will use the TPM to unwrap it, and when you try to read it back, again, it will be wrapped again. But don't use that for all your keys, because TPMs are slow, and actually we found it's quite an unreliable device at scale, so you don't want to use it for all the keys. So you can do like a combined schema approach. So so you have some kind of like provisional process, right? You have your cloud HSM or KMS system. You have some kind of root key for a server, and you wrap it to a particular machine, to its TPM. You have a wrapped root key. You send it to provisioner. The provisioner will insert it in the kernel and wrap. And the kernel will unwrap it with the TPM, but you do it only once, like per boot, right? And then all the other application keys are being sent wrapped with this root key, and they're like unwrapped with the like encrypted keys. And there you will basically you will only use the TPM once per boot, and then you will use software decryption for everything else. So it's kind of better. Cool, right? But yeah, but there is some problems with this approach as well at scale. So applications will never see the plain text cryptographic material, but applications are still somehow responsible for contacting with the centralized KMS HSM system. So who uses Vault, for example? Yeah, someone uses AWS KMS, and it's a nightmare, right? So like if you adopt Vault, like every application needs to be able to talk to Vault, and everyone needs to integrate the Vault SDK, and then you decide to migrate to something else, and everyone has to migrate to something else. Yeah, so your application needs to know how to reach the centralized KMS, HSM, or whatever key management system you use, It has to encode its URI in this configuration file, and then you have to bundle that application code or SDK into your code to actually talk to it. And the problem is like this little administrative control of the created key objects. So applications are responsible for grabbing these wrap blobs, putting into the kernel, but if they set incorrect permissions, then everyone on the system can go and read those keys, or use them at least, which is not what we want. And yeah, KMS ideally needs to somehow authenticate each requesting application from a particular server, which is also a good thing. So there is a better way in Linux. So far, there are actually two system calls you can use to insert keys into the kernel. So far, we have been using underneath the add key system call. And the semantics of add key system call is basically, application says, I have a key, hey kernel, here's my key. And that key can be plain text key if it's a user key, or an encrypted blob if it's an encrypted or trusted key, but still application somehow needs to have this data, right? There is a different, more interesting system call called request key, and the semantics here is better, where application doesn't have anything. It says, the only thing it says like, hey kernel, give me my key. And the kernel is somehow responsible to figure it out. Right. The way how it works is basically, yeah, the process wants to have a key. The only thing the process needs to know is like a free-form string ID for a key. So let's say a process can say, I want a key for cloud at key 1, and it sends the system call, requests the kernel to do it for the system call. The kernel itself creates like this special placeholder for a key, but obviously everyone's setup is different and your kernel doesn't know where you should get the keys from, and that's why you should help it a little bit. So what the kernel does, it requests user space for help, and it does a so-called call-out process. So it calls an executable located at as-been request key, and if you use your distro standard distribution, you already have that binary there, but again, the binary itself doesn't know where to get the keys from, so you can actually write extensions to it, and you can write several extensions based on the ID of the key. So for example, you may have extensions where you can get the keys from HSM, extension will gain keys from cloud, or some test extension you can use for testing. So if the process requested a key for the cloud, then it will be routed to the cloud module, and this module knows how to contact the cloud HSM. It will get the key and basically shuffle it back to the kernel, and when the kernel receives the actual key, it will notify the application that your key is ready, here's your ID, now you can use it. So yeah, with request key, you have like this single centralized operating system API to request keys for application. And your application is fully decoupled from your key management, right? So there is no KMS, HSM connection strings, no URIs, nothing, just a plain system called give me my key and free-form string ID. Yeah, and it's fully decoupled from storage backends, and as an admin, you can easily migrate from one backend to another without any changes to your consumer applications with no code changes. And it's a more secure way to instantiate keys. The way how all that process works, that actually the kernel has a special set of credentials which allows only that has-been request key to instantiate keys, so there is like little room for attackers like chiming in and stealing the information. So yeah, basically with request key support, the key management and distribution becomes like this, the core service of the operating system. I wanted to show my example on take on this, so I wrote one of the plugins which allows you to generate application-specific keys based on your TPM. So it's kind of like it turns your server or laptop into more like a mobile device where you have device-specific keys, but like you have a unique key for every application. It's a proof of concept now, so it was written in Python and not a real programming language, but still you can go and download it and experiment with it. So here's an example. Like if you download my code, don't bother too much about, this is how you configure basically your request key plugin. So what it says is like, if some application tries to create a key which starts with an ID that starts with TPM2 derived, call this plugin. And this is where, even though the request key program itself is written in C, you can actually write plugins in any programming language. It can be a Bash script, a Python script, a Go program, whatever you like, a JavaScript. Yeah. So just call my plugin, and my plugin will be responsible. And what my plugin can do, it basically creates application unique keys based on the metadata of the application itself. I will just show you in a moment. So the first example, what I can show you is, imagine we have an application, which I'll just use the keyctl. It requests a key from the kernel. It requests a user key. It's called TPM2 derived test. And these are parameters 32 and path, which are passed to my plugin. And what they mean is create basically a key of length 30 bytes and use the application path as this unique metadata identifier for the key. So yeah, it will work. The kernel will create the key. And now I can print the contents of the key, so I can see I have some key, right? So I can now delete it, right? And recreate it again. So I'm requesting another key with the same parameters, and you can see that from the kernel perspective, this is a different key object because the serial number is different. But if I print the data again, it has the same contents, right? So I'm creating these, based on my current TPM, I'm creating an application static key specifically for the application key CTL, which is located at user bin CTL. So to prove this, again, I can remove that key, and what I can do is I actually can move my requesting application from one path to another. So I'm moving it from my user bin to my home directory. And if I repeat the request again, I'll get a different key, but now the key contents will be successfully different. So now you have this powerful concept of like every executable on your system has a system unique key for itself based on your TPM. So you're getting hardware security also out of the box because you're using TPM to create these keys, but actually it's fully decoupled because the keyctl utility doesn't even know how to talk to TPM because it goes through the kernel has all the bits and pieces. Cool? Yeah. Yeah, and I also wanted to show that it also takes into account your user ID. If I basically run the same thing but with a different user, like let's say is root, you will get a different key as well. So this is very powerful concept. For example, let's imagine you have an embedded system, right? And you have a read-only file system, but you still want to have a static SSH server key. So when you connect to your router, you don't have to re-accept the key over and over again. So you can actually use this concept because you don't need even a writable file system. You still will have a device unique SSH key, which will be available only to user bin SSHD and nothing else. There is a second mode in my plugin I wanted to show. So instead of the path metadata, here I can ask my plugin to generate based on the application checksum, so the application code itself. And it's also very powerful because, yeah, I can generate the key, I can read it, I can delete it. Now I can copy the key from one place to another, and I can generate the key again, and it will be the same key because it doesn't take into account the path now, but actually the requesting application. And to show that it works, I'll delete it again. Now I'm patching my application. So I did some previous research, and the keyctl utility has bad message as an error string embedded in the executable. So I'm just patching it from bad message to bad massage. I'm replacing one letter, right? It will still work. So now if I use the same application to create the key will be completely different. So my key is cryptographically bound to the requesting executable code itself, no matter where it is. I think this is all I wanted to show. So yeah, Linux kernel key retention service is very flexible and gives you like this nice building block to build sophisticated and secure key management system on your Linux platform. Here are some links, I think like most of them, to kernel documentation and man pages for different keys and keyring types. And everything that I presented here today and more with the patch to OpenSSH and some other interesting bits are located in the Cloudflare blog post that you can go and read. Thank you very much, and I'm happy to take questions.
Thank you, Ignat. This whole process must be particularly useful at scale because you don't have to rely, as you've shown, on a TPM slowing things down. And since it's in kernel, it makes it a lot faster.
I can see also this is very applicable to private cloud environments. Actually, some say it's a bug, but it may be a feature that keystore is not fully namespaced. So for user, it only namespace based on user namespaces. So technically, you can have a host-wide plugin for your Kubernetes cluster, and you don't have to use all the Kubernetes secret crap. You can configure your Kubernetes host to actually use this plugin, and every container in your application can similarly use the same technique to request container-specific keys or anything else that you want to do. Like they don't need to talk to it, and you don't have to have sidecars in your containers. They can just ask the kernel directly, and it will be handled by the host itself. So the host will know how to provision keys for all their containers. So yeah, I can see that happening. And this is like what I mentioned yesterday. I was really excited by this technology. This is why I became a maintainer for it recently, because I wanted to push it forward, but there was not a lot of support from the upstream community there, so they said, okay, if you want to take it. So I can hope to make it better.
Excellent.
You mentioned TPMs is slower compared to having a software keys in the kernel. I'm wondering how slow it is, or which form latency to get you the key or bandwidth of requests.
Well, I would say it depends on probably TPM, but TPM by design, the reason they are present in every computing device these days because they're really, really cheap. And really, really cheap means they're not really, really powerful. So let's say if you want to build if you want to store your TLS private key in the TPM on your high-performance web server, most likely it won't work. It will be just slow. So this is where TPMs are more likely to store like key encryption keys rather than data encryption keys, if that makes sense. And also, depending on the vendors, we found some vendors quite unreliable, so you hammer a lot of requests to the TPM, they just break and you have to replace them, at least on the server.
What about ARM offering for trusted execution environment or OPT or these kinds of
I think I never researched it deep enough, but the kernel code actually has keystore support for ARM for OPTE, the open source trusted. So like there is code in the kernel which allows you to store keys in the trust zone. But actually you can also write your own user space plugins to somehow communicate with it, so depending if you have that interface.
I feel like I'm hogging the mic here, but one more question. So I saw that the kernel object or the kernel do call back to the user space. So how secure is this callback, and can you maybe call to a process that spoofs something or try to inject wrong keys?
Well, I mean, if you're able to replace a process or executable at has-been request key, you can actually get malicious there. So yeah, but there is some protection that once the kernel called that executable, only that process can create that key, so you cannot have a different process, even if it's the same executable, actually going and spoofing that key, if that makes sense. So as long as you trust the executable located as has been request key, it's kind of secure. I understand it's maybe not ideal, so all the concept I presented today with the TPM, I actually tried it to push as a kernel patch set to actually do everything like with application unique keys in the kernel, so it never even calls out to user space. So this is where you get better security, that you request the operating system for a key and you get a key from the TPM with no user space involved, so you have less friction point. But it's still like early to convince to push it through.
So I'm wondering if there's integration of iViewing and in the context of being able to sign packets they are sending to another server, so the server can verify that is coming from you, but that is handling kernel side rather than in user space.
Sign packets?
So let's say I'm sending, since I can already filter packets through eBPF, for example, in the kernel side, if I want to communicate with another server, but I want to make sure that I also communicate the signature of the data that I'm sending, so that server can verify the integrity of the data and that is coming from the server that it expects. Can that requires you to sign the data currently in the user space and then validate it on the other side with the application. Is it possible to store that key in the kernel's keystore and have it so that when the application is sending data, that is signed on the kernel side before it's sent to the across the network to the other server, rather than handling it on application side in user space?
Okay, I get it. No, I mean, you can only, basically, you can store the key and you can sign the data, but you need to get the signed data out and send it yourself. No, I mean, that's not possible. There is also what I didn't mention here. Now we actually push the patch search from Linux 6.1. What is possible is to actually do symmetric encryption as well. So if you have like a trusted key or encrypted key, you put it into the kernel and use the serial number to encrypt and decrypt data. But again, you have to communicate with the kernel. So you send the data, you get the response back, and then you're responsible for sending it again. So there is no like, probably you mentioned like a send file system call where it can like sign and send it again. So yeah, you have to traverse the Linux, the kernel space and user space barrier several times.
Okay. So you mentioned this key rings that calls binary user space. Are we concerned about this interface? How does it work with bound namespaces and so on? I mean,
actually, it's not the only example of such thing in the kernel. So there is like several. They have this even special framework called call-out processes. So for keys, it has been request key. There is a similar process for kernel drivers which require external firmware or request firmware, so it's kind of like it's a standard partner actually. So I don't think it's namespace in the sense it will always call to the initial mount namespace, so you cannot use mount namespaces to basically hijack it. If that,
yeah, I was just wondering how that would work in a container environment where you might have.
No, it will always call into the host namespace. Initial mount namespace. I think another example is core dump processing. You can also like do a call out in user space and send a core dump.
Thank you for the presentation. I'm also trying to understand the difference between this and HSM. Or HSM was a BTCS development interface. So this is not a replacement for that. We can say it's a complementary thing for in-memory protection when you load the key actually and start using it in the application level.
So technically, you could BTCS interface is a standard interface to access cryptographic devices which might be hardware or software, right? Theoretically, you can implement PKCS interface on top of Linux kernel syscalls and call it a day, right? Yeah, but like, I mean, PKCS interface is kind of like a standard for accessing devices, and most HSMs provide it. And these are basically underlying building blocks of the Linux kernel, which you can use either directly or you can then call PKCS interface on top. But this gives, like, for example, a crypto library might implement a PKCS 11 interface, and from that perspective, your cryptographic keys will still be in your address memory space, versus if you use this, it will be in the kernel space, memory address space. So you're better protected from the, if your code suddenly becomes like malicious or something.
Okay, but we still need a resistant storage, right? With this solution, we still need an HSM or...
No, like technically, it depends on like your requirements. Like in the example they just showed you, don't need an HSM. It's enough to have a TPM system, and it will always work because like most systems have TPMs. But if you're building like an infrastructure key management system, of course, and you have like a centralized key storage where you want to store your keys, like in the cloud or HSM, you can use that as well. So you don't have to, but you can.
Hello, thanks for the talk. I wonder, I like the way you used the plug-in to use the TPM and the application binary in itself with a checksum. That's exactly what we do too, it is tiki. But I wonder, of course, what kind of checksum did you use? We use LakeTwist. What do you use?
You use what, sorry?
What kind of checksum did you use?
SHA-256, basically.
Okay.
Take the file, hash it.
Yes, we do the same thing with LakeTwist in the tiki.
My kernel version of that was actually hooking into the Linux IMA subsystem. So you like Linux kernel itself, if you have it in your configuration file, can hash your executables before every time it executes them. So like you can just take that hash already. But again, it's the same SHA-256 hash.
Cool. Thanks.
Fantastic. Well,
Thank you.
since I see no more other questions, thank you very much. We've stopped at the perfect time.
Thank you.